and then you will have a short, okay, thanks. And then you'll have your slide, and then I'll introduce Ken, and then we can start. Or maybe I can just directly start. So good morning, everyone. As usual, we have our weekly seminar today with our guest, Dr. Kyungnam Kim today. And thank you all for attending today's seminar. Here also you can see some of our upcoming seminars, and hopefully you can check and mark them on your calendar in case the topics are relevant to your research area. As I said, today we have our seminar titled Digital Biomarker Discovery for Voice and Mental Disorder. And our speaker is Dr. Kyungnam Kim. Dr. Kim graduated from University of Maryland under Professor Larry Davis, and he has extensive industry research, and in the past 20 years, he's led several industrial projects with research and development nature, and currently he's a vice president at SK Telecom, which is a very large mobile company in South Korea. It's a company that developed 5G technology in commercial capacity for the first time, and is very active in using AI to improve their technologies. Dr. Kim and I have a prior collaboration, and I'm very happy and excited to see him presenting his current research today. With that being said, I'll leave the stage to Dr. Kim.
All right. Thank you, Mohammed. So let me share my screen here. Can you guys see the slide okay in pre-screen?
Yes.
All right, so hi everyone, my name is Kyungnam Kim. I go by Ken, so you can call me Ken. I am vice president at SK Telecom. For those who don't know SK Telecom, let me tell a little bit about the company. It is the largest mobile network operators in Korea. We have 50% of share in the country. You can think of it's like a Verizon or AT&T in US. What we did was world first 5G commercialization in April 2019. We also a major shareholder of the SK Hynix, which is the second largest memory chip maker, and also third largest semiconductor companies in the world. Our company is diligently working on other areas too. We are working on commerce and security, and also media. Today, we'll talk about a new area we are investigating, healthcare, which is digital healthcare using AI and digital transformation techniques. We recently start to investigate our digital biomarker development. So today, it will be early stage of our development with our hospital partners. But I will talk about why we are doing, what we have been doing, and also how we do, and some research with our future direction. So great, let me start. All right, so the contents of the talk will be like this. I will introduce what biomarker discovery problem we are working on. We also talk about previous work, and we will talk about our framework using the multimodal data to detect the voice and mental disorders. I also talk about data collection, how we did it, how much we collected, and also I will talk about some data analysis with modeling results we have. And I will conclude with our future direction to build up a healthcare service platform. So here we have our own team, the group of people who are working on this project. We also have other partner organization like several hospitals here. As SK Telecom, can you see the screen okay?
Yes.
Yeah, I have a little bit problem here. Okay, so anyway, we have 3 other hospitals. One of them is Severance Hospital, otolaryngology department. Otolaryngology means ear, nose, throat doctor. So you know, as you know, ENT, and also psychiatry department in Severance Hospital, and also psychiatry department in SNU Hospital. Among others, Yoon Kim is a CTO of our company. He used to lead Shiri airport in Apple. So here, I will try to explain why we are doing this. As you know, COVID-19 changed everything. So it drive a new way of our healthcare service. So today, many people try to use digital technology as much as possible to address health care issue everywhere in our daily lives. So for those people who are aging these days, they need some remote way to address their health problem. So telemedicine is quite useful, and it will be pretty popular in the future. The next chart is about the how we address the health problem using what kind of indicator. So biomarker. Biomarker is some quantifiable measure of certain health status. Usually classical traditional biomarkers are blood pressure, heart rate, and x-rays. So those can be used to tell how healthy the people are. Usually when doctors decide or tell what kind of health problem people has, some study says non-clinical factors can account 60% of the health determinant. Sorry. So as you see on the chart, behavior and social circumstances and environmental and physical influences. So those non-clinical factors could be also important to tell the your problem or status of your health. On the right side, you see some graphs of the digital biomarker market. Today, also earlier, it was not that large, but it's increasing with a pretty good rate of the growth ratio. So compounded annualized growth rate is about 40%. So it will become pretty big in the future. So digital biomarker development could be a pretty big game changer in the future in digital healthcare. So we believe digital biomarker can be developed using advanced AI and machine learning technology, leveraging the smart devices today and also big data analytics. As you see in the chart, we are not the only one who are working on this problem. Like the Biogen Apple, they are working on the mild cognitive impairment detection problem, and also the Aura. Aura is the company who is making the ring. So, I mean, you wear the ring every day, every time to monitor your health. So they are also working on the UCSF. I mean, these companies are working together to develop the digital biomarker or the digital healthcare. We believe the key of digital biomarker development is the close collaboration with the medical expert in the area. So that's why we are working on several major hospitals in Korea to collect the relevant data and get some help from their expertise to guide the direction in the right way. So I will talk about the digital biomarkers, specifically what kind of problem we are working on. So first is voice disorder. Like some problem related to your vocal cord. So we are working on voice diseases like a glottal insufficiency based on multimodal data we are collecting. It could be voice and also EGG. EGG is electroglottography signal. Some of them may know the EEG. EGG is the same version, but it tried to detect the change you have in vocal fold. So we are also collecting those data. Specifically, we are collaborating with otolaryngology department of Severance Hospital here in Korea. In this world, to detect the voice disorder before, doctors usually use ear, nose, and throat endoscopy, which is invasive. You have to put those endoscopy into your vocal cord. Another set of equipment, it would be sound wave analysis equipment. It's a sort of a classical way to detect certain change in your voice signal, but the setup that the hospital had is pretty cumbersome and pretty time consuming. And also it didn't capture the full potential of the signal or whatever the patient has into the analyzable data. So what we are trying to do is a new digitized voice disorder biomarker by extracting pretty carefully engineered feature and the method to analyze them automatically. Also, we are collecting EGG using the pretty advanced material technology. So here, just a second. Oh, wait. The second thing we try to address is a mental disorder. Usually, doctors use the self-report or survey by questioning several standard questions to the patient, and also relying on what they answer. So this is how the mental disorder has been addressed. But we try to detect or give the doctor some, quantifiable measure to manage how their patients doing by objectively measure their voice and also biosignal by having the smart watch or the smart wristband, so that it's pretty consistent. Also, patient may not need to go to hospital to be checked, but also they can wear those devices and check their mental change everywhere, every time. So that's how we are aiming to develop our digital biomarker for mental disorder.
I have a question. This is Keith Burkhardt, and I'm wondering, for these digital biomarkers, you need to, I would assume, determine their validity with some ground truth, and presumably the ground truth is self-reports, right? So it's just that you'd rely less on self-reports. Is that the goal? Or I mean, are you saying that this is a way to completely avoid self-reports altogether?
Oh, you mean you're asking me, are we using self-report too with the other data?
Well, I mean to say, for the digital biomarkers, I was thinking, maybe incorrectly, that the digital biomarkers would correspond to, say, mental health based on some ground truth data like self-reports. Or are you just feeding in these signals, sending these signals to the doctors, and they are interpreting the whether it's
oh, I see. So what in the our data collection protocol, what we are measuring is also the other indicator, not the self-report. One of them is there's some pretty reliable measure. I have to think about it. It's not only subjectively collected by answers that patients give. It also measure the other what was it? It's a I think it's a temperature or something. So when you put in under certain disorder or stressful situation, they can match that to the ground truth of the disorder or the severity of the disorder.
I see. Thank you.
Yeah. So
yeah, in other words, that we can avoid self-reports altogether. That was my question, and yeah, it sounds like that.
Okay. All right. So actually, you know what, the next third thing that we are working with our hospital partner is the stress. It'll be pretty much like the mental disorder before, but we specifically trying to detect stress, mainly because everyone here and anywhere could have stress in many ways, right? So as you know, the stress is a big issue in the sense of the many people are having this, and also a lot of economical loss could caused by the depression or stress. And some says, we are losing, or that we actually spending a lot of health cost due to the stress handling and management. On the right side, you see the graph. This is about the how people are managing their stress. First, when you get certain influence of having the stress, and we actually less resistant, meaning it could be very stressful. So, but when you getting that stressful impact to you as time goes by, you are pretty good at overcoming the stress. So you are resistant. But after a certain time, you just gave up. So it'll be pretty bad to handle certain stress. So this is a pretty well-known stress graph that was developed by the expert in that area. All right. So overall, what we are trying to do is developing digital biomarker to detect the voice disorders and mental disorders using several different types of signal that we can collect, but easily, and also always, almost always. So we are trying to use the voice and text and also other biosignals like blood pressure, heart rate, in our specific case, EGG, that captured the electric change in your vocal cord. So we are trying to build up a voice biomarker and language biomarker and biosignal biomarker. As I explained earlier, we think it will be a lot more efficient and effective compared to traditional self-report or cumbersome equipment-based measurement to address this health problem. Also, as I noted earlier, today many people are wearing smart devices like a smartwatch or wristband. So those can be used to collect the data and also monitor or even tell you, any symptom you could have in your health problem. So the remaining part of the talk, we'll talk about the actual data and our technique to detect certain types of the disorders using the state-of-the-art machine learning techniques.
Just a quick question.
Yes.
So let's see, this is a little out of my area, but isn't the gold standard for stress measurement basically doing blood tests and looking at hormone levels? And if I've got that right, then do you validate against that in terms of looking at correlations between your biomarkers and stress levels? Does that make sense?
To answer your question, a good question. Especially blood pressure, I do not know. We try to find what kind of measures are relevant to each biomarker.
Mm-hmm.
So we believe the EGG is relevant,
Okay.
and also the voice change relevant, especially for our voice disorder problem. But blood pressure, not sure.
Well, also, I was just curious about hormone levels. So like cortisol, is it cortisol?
Oh, yeah. Now I remember the cortisol is being used to construct our ground truth for the stress.
Right, exactly. Yeah. Okay, good. So that is your ground truth measurement for stress level.
Yes.
Okay, that's exactly what I want to know. Thank you.
Yeah, sorry, I didn't. It didn't came up when another question came up. So the cortisol is the indicator. All right. So let me talk about some piece of the work that was done earlier. Here, this is about the piece of the work done earlier to measure the several different activity of a person by using bio or wearable sensor. So this is a pretty conceptual diagram of what they're doing. So the by having certain type of sensor on your body, time series data being captured, and also you can capture the image or voice sound too. So you using whatever model you have, you can detect what the person is doing, is climbing upstairs or the running and riding a bike, etc. So this is today. I mean, it's not especially interested here, but I'm trying to tell this can be done using the lot of sensor available today. The second piece of the previous work is about the voice disorder prediction. So the reason I brought up this work in my presentation is because this might be the one of the closest work I believe to our approach and then problem addressing. So what they did was they used the medical feature, whatever the metadata they can collect, and also the voice feature collected from the voice signal. So apparently what they did was they constructed a separate model for medical features understanding and then voice feature understanding to tell whatever the disorder they trying to classify. Key thing about their approach is they try to combine each decision from each model to come up with whatever final prediction label. So it's a decision level fusion, and also they are using pretty simple acoustic feature only from the voice signal. So this is one of the work related to the voice odor detection. This paper is talking about the way of the fusion. So they're working on the one of the multimodal fusion technique that use the imaging and also other health record in their multimodal approach. What I'm trying to talk about in this chart is this: when you try to combine multimodal data or their model results, you can do three ways. One, it's a feature level fusion. When you have multimodal data like image, metadata, or voice, what you do is you just put together all the features in one bucket, or the pretty large input data. It can be fed into a single large model you can construct. So it's a relatively easy to architect the model, but it'll take lots of time. So you just rely on the model to figure out what the interrelationship between feature and how you separate the space into the desirable separating model. The second way of addressing this problem is decision level. I think you can imagine what this does by having missing the name. Like the work before I talked about, they try to build a separate model for each modality, and then they put together the decision into one by using whatever high level method of the combination. You can do best boosting or the bagging method. The last method is the hybrid level fusion. Intermediate fusion can do, you can construct the certain types of the feature, and then it'll have a separate model, but it doesn't give you direct label or the answer immediately. You have an intermediate representation. You can combine those to come up with your final results and predicted label. So we believe this is the pretty good way to address our problem. by having advantages for both mothers. As you know, when you do the decision level only, you may lose hidden relationship, whatever correlation between modality. So we try to capture using this hybrid or intermediate level fusion. So that's we are trying to address our problem. So here I will talk about what we've been doing by using multimodal AI technique to address the digital biomarker development for the voice and mental disorder. So conceptually, we are collecting the voice, and also we have, usually for the mental disorder problem, we have a pretty standardized questionnaires to ask patient, and also certain types of the standard paragraph for the patient or any people should read. So we extract the language data to understand the what their mental status, etc. Another notable thing here is Neckband. Like I said, we are trying to collect the biosignal data easily, comfortably, and also almost always. So we are trying to build a smart mobile devices, which is a neckband. So this device can be wear around your neck, but it's contacting your skin of the neck area to collect a few different biosignals, mostly EGG, like I mentioned. So this data in the development stage, we are putting into our data storage using cloud, and they are transferred from our hospital to our data storage in a secure fashion. So we can run our model and the developed model over those data. So we are extracting voice feature and linguistic feature and also biosignal feature to add into the multimodal AI model to get the prediction of the voice or mental disorder. This smart neckband is being developed using pretty advanced material. It should be capturing the electro signal very subtle, pretty reliably using low swap hardware. So it should be small, low weight, and also low power. But I wouldn't talk about too much about the neckband today. So let me tell you why we think we can do this. We believe we are expert in the voice understanding, language understanding, and also the machine learning using the AutoML platform that we have. So SK Telecom has the Korean version of BOT model, and also the automatic machine learning platform too. So these hospitals are expert in the ENT problem and also psychiatry problem too. So we are working together. We are building our machine learning model, and our hospital partners guide us the right direction by doing the clinical validation and data collection. So let me go a little bit deeper to our model actually. So as you see, we are collecting some of the metadata, also the medical information of the patient or the whatever subject, and voice signal and biosignal. So when it comes to the feature level, we are constructing the metadata together, and acoustic feature and spectrogram, and also raw PCM signal, and also the linguistic feature. The coloring of this, the architecture indicating the dark, the black-like box is what we been already doing, and the light gray boxes are what we are working on, but we haven't done that yet. But this is the overall architecture of our approach to come up with a multimodal answer of the voice and mental disorder. So let me talk about a little bit more about later after I presenting the what we already did. So I will come back to this chart again. So this is a pretty relatively long-term project. It's a multi-year project. We are in phase 1, doing the biomarker development and data collection, things like that. Next year, 2022, we will be finishing up our machine learning algorithm based on what we've been discovered this year, what's being used for the voice biomarker and other biomarker. And we will be build up the model and the software by next year. And then in the phase 2, we will be seriously working on the approval process of our digital biomarker by having our software and model validated and also approved. So this is the entire schedule of our work. So this is a data collection. Like I said, we are collecting data, the voice data and other biosignal data based on the clinical studies that was done by our partner hospital. We think this as 3 phases. One is data collection for model building and collection for the validation of the model. And also finally, the software. We call it software as medical devices, SAMD. We collect the data for this. So in the clinical field, they call it retrospective study up to the prospective study. And also the validation, we use other hospital data too. So the amount of data is about 12,000 in model building and 2,000 sample and model validation and 400 for the final software validation. Notably, you may note that it's the data the partner has been collected for 20 years. So we are relying on this data. This is actually the picture of the data collection today. It's not so modern, but they are still using this in their hospital. The mental disorder data collection, we talked about the how you actually rely on the validity of the ground truth. We talked about corridor before. Another thing, what we are doing is real life data collection. We think whatever the real mental disorder or other problem like a stress could come in your daily lives. So what we are doing is we have people wear the smart device. It is this wristband. They are actually collecting their data entire their daily activities. So we also ask people what they think by using the mobile app, so that they can actually enter whatever they think, whatever their mentor or the status they are having now. So we also collecting real life data too. Here is our data detail. I will talk about what kind of disorder problem we are trying to classify. But let me tell you, we have 3 different levels. The level 1, we just simply say, oh, this is a normal, or this is a patient, or they have problem. Another area is undetermined. The second level of classification is 8 voice disorder groups. This is the 8 representing groups of the disorder that the doctors chose. They believe these 8 groups are pretty important to classify. The class number 3 is deeper down to the specific disease. So we chose specific disease. We believe we can detect by using digital biomarker. So these are the different levels of classes that we are trying to classify. On the right side, you see the feature that we have. Some of them user data they collect, and also the self-questionnaire, actual acoustic feature, and also voice recording themselves, and also biosensor data. These are our 8 disorder groups. So benign, vocal mass, malignant, vocal mass, up to the inflammatory disease too. So dysphonia. The dysphonia is the problem in the class 1 that we worked on the experimental results. Okay, so here's the actual analysis and modeling result. Let me tell you, this is an early stage of our work, so it could be not much, but I will talk about what challenge we had and the results we got. What we found was the data we collected is unbalanced. I will tell you what that means later. And also the labels are ambiguous, and when you compare your data, you see a lot of overlapping boundary among the feature. So it's pretty indistinguishable. And also the result, we have 2 sets of results. One is the binary classification of detecting the dysphonia, and the second result is a multi voice order diagnosis classification. All right, so like I said, we have lots of voice data collected from our collaborating hospital. As you see, if you think about the hospital, who would be the most people coming to the hospital? Patients, right? So a lot of data from patient, but not much from the normal people. So to address this problem, what we've been trying to do is balancing between those 2 distributions. We are doing undersampling. We also generating synthetic sample out of the sets of data. So here the undersampling. So lots of patient data with little normal people data. We are collecting randomly sampling from the patient distribution to get the equal or similar amount of the data compared to the patient. I'm sorry, this is mislabeled. This is a patient, this is normal, sorry about that. And another way to mitigating this issue is the generating new samples. So from the less data distribution, we are creating new samples of data by using nearest neighborhood technique. Specifically, we are using synthetic minority oversampling technique to come up with some sort of the balanced data distribution between these two, also among others. So these two ways of the handling this unbalanced data problem, we found that it's somewhat effective to deal with to come up with the classification model. Another issue challenge we have in this data set is the when you look at the feature, this is the graphs we drew using the selected feature in 2 dimensions. One of them is a positive sample, another is a negative sample. They are pretty much overlapping. So what we did was, out of the samples we have, we are trying to select pretty good, strong samples out of them. So this x-axis is a clinician-based dysphonia severity index. So we chose pretty normal case and pretty serious case only. So we exclude some ambiguous data sample out of our classification training. Another way to solve this problem is we are not relying on the acoustic features that other papers are using. We are introducing a new set of features. We're trying to find what features are pretty relevant to the voice disorder. So we are constructing a lot more the features out of the voice signal itself. Oh, another thing I didn't mention, I forgot to mention, is our results mainly about the voice disorder detection problem. We haven't collected enough for the mental disorder yet. So unfortunately, I wouldn't be able to talk about the mental disorder results. So I will talk about the first set of the results, binary classification for detection of dysphonia. Dysphonia is the problem, one of the major problem that the ENT or the voice patient has. So it means that you have a problem with your voice. So like I said, we apply these 2 techniques to deal with unbalanced data set and ambiguous labels. We use 33 acoustic features we got from the voice signal equipment, analysis equipment, and also other metadata. So we simply apply the panelized logistical regression. So we also use the penalty term to avoid overfitting. So what we did was we tried to collect 10 different sample sets to train a certain model. So we did it 10 times with the 90% training, 10% testing. So we averaged the 10 times of our test to come up with this average number. So precision recall, recall is pretty good. So we believe this recall number is good enough to tell if you have the voice problem or not. The precision is not that bad, so 88. So overall, the accuracy is 90%. So for this specific case of telling the dysphonia or not dysphonia is pretty promising. The The second set of results is more complicated, but it's pretty good to work on. So we are trying to classify multiple specific voice disorder. This is actually class 2 or class 3. Class 2 is about the voice disorder groups of the voice disorder. Class 3 is specific voice disorder. Sorry. So in this problem, we are building up the set of the model and also the way combining those. We use the, as I talked before, the usual category index metadata and also the classic acoustic feature. On top of those, we use the spectrogram feature that we developed on our own by constructing 685 features from the spectrogram. And we used augmentation technique to balance between different types of the disorder data distribution. And notably, what we had is acoustic encoding model using the DNN, converting these spectrogram features into 6 different coefficients that can be fed into our fusion model using the XGBoost to actually produce our final prediction label. So this is the architecture of our multiple voice disorder classification. On the right side, you see our precision and recall numbers. Notably, some voice disorder problem can be separable better than other disorder. So by doing this, we will know what kind of voice disorder can be detectable easily or reliably than others too. So overall, class level 2, we achieved accuracy 71%, level 3, 72%. So it's summarizing our approach in overall hybrid multimodal fusion. Like I said, we have our NLP, natural language processing engine in our company. So we are trying to use linguistic feature too. And also by using the low PCM signal of the voice, we are trying to capture whatever hidden feature that voice signal has by using the transformer model. So our plan is to construct the sort of intermediate model for each feature or modality feature, and having this into the fusion model, combining those model generated representation. There could be 2 ways. We can fuse whatever the voice order probability in a vector of the output for each model. We can combine those into the final model using the XGBoost, or we can use the projection technique. We can build up a high dimensional disease space where each feature data can be projected so that each disease can be clustered, but it could be separating each other. So we are thinking about that approach too. So we continue to develop this whole architecture by filling up the missing pieces. Right, so it's been pretty much about 1 hour. So what remaining thing we do is we try to build up the service platform where patient and doctors can interact by exchanging the data and giving you some diagnosis advice, etc. So the long-term vision that we have, we think by combining AI technique and wearables technique, things like that, we believe we can address health problem easily, comfortably on a daily basis. We think we can extend to life care service for any people, not just the patient. So it's been about 1 hour. I think we can take 1 or 2 questions.
Thank you. So in case of questions, you can type in the chat box. Okay. Okay. Thank you so much. It seems that we don't have any question at this point, and several of people that you are going to meet later have attended, and I think you can probably elaborate during your meetings.
Sure. All right. So it's been my pleasure to be here. Thanks, Mohammed, for invitation. I think, yeah, we can make more progress and to report more exciting results later.
Sure. And would you be able to share your slides with us? So because I got an inquiry that people might want to check them later.
Oh yeah, I will tell you later. Yes.
Okay. Thank you.
All right.
Thank you all, and we'll meet again next week.